Hello everyone. Welcome to this lecture in the Decision Trees from Scratch series. In the past 5 to 6 lectures, we have looked at classification trees and we have looked at building an entire classification tree from scratch and also coding it out in Python. Today, we are going to start a new topic which is regression trees. So, for the longest time, I thought that classification is the only purpose of decision trees. I did not know that decision trees can be used for regression tasks as well. In fact, what I learned about this is that they are very useful and very impactful in a lot of real world regression problems. Let's look at some of these problems. So this is the very famous John Hopkins dashboard for COVID-19 cases. If you look at the red spots, you will see the concentration of where the infected cases were. In fact, many famous forums such as the World Economic Forum converted this into a live animation to show how the infection was spreading. So if you look at this animation here, you will see how the red dots evolved. They started from China and then different places around the world started developing these big red spots, which means the infection size was progressing slowly in all the regions of the world. New York Times maintained a very nice data set about this. Here you can see how the infections varied in different continents of the world. There are multiple peaks, and here you can see the hot spots where the cases were maximum. You can even plot cases per capita, deaths per capita. You will see areas which are very dark in color, which means COVID 19 really had a huge impact in that particular area. Now, when COVID 19 was progressing, there was a big need for governmental agencies and policymakers to really predict how many infected case counts will be there in this week, next week, and the week after that, because that decision would also influence the policies which they would implement, such as the mask mandate, the lockdown policy. How long should the lockdown be implemented for? Whether masks should be compulsory, in which areas should be compulsory. For these reasons, forecasting became very essential, and Kaggle played a very important role. So Kaggle started having these challenges during the COVID time. So here you can see COVID-19 global forecasting challenge, and so many people submitted their solutions. So if you look at the challenge itself, the forecasting task. So this was a forecasting task essentially. The challenge was to predict the infected cases as a function of time. So if you look at the data over here, you will see that in this challenge, you will be predicting the cumulative number of confirmed COVID 19 cases in various locations across the world. So they have the training data, they have the submit testing data, and you have to submit your solution. Number of solutions were proposed, but what is very interesting to see is that regression trees were also used to make these solutions. Earlier, I would have thought that people would have proposed solutions using least square methods, gradient boosting, some complex ML algorithms like neural networks, etc. But even regression trees was used to propose the solution, and you can see here this solution as a silver star here, which means that it was liked and upvoted by many people. And I'll share this notebook in the information section of this video as well. But I just want to illustrate here that regression trees can be used to solve even impactful and real life problems like the COVID-19 pandemic. So what you are learning in this lecture will be extremely beneficial for you. Not just this problem, you will see that on GitHub and on Kaggle also there are a number of projects which have been done with regression trees. For example, there is a famous petrol consumption data set, which is basically about different things such as petrol tax, highways, population, and then ultimately the goal is to predict the amount of petrol consumption, right? And it turns out regression trees is very popularly used to solve this problem. It's also available on Kaggle as I'm showing here right now. People have written many codes for this. If you search regression tree on GitHub right now, even after this lecture or during this lecture, you'll get so many projects which have been done using regression trees itself. So the purpose of this lecture is to first give you a fundamental understanding of what really are regression trees. And then similar to the way we approached for classification trees, we'll be building out an entire regression tree from scratch. And then we'll also code out a regression tree in Python. So let's get started with today's lecture. First, I want to tell you a bit about why regression trees are beneficial when you have so many other methods for regression, such as the least squares, the ordinary least square, etc. One major reason which I found out is that regression trees can handle non-linear data in a much better manner than other regression methods. So let me explain to you what I mean. Look at this data set, right? This data set looks pretty much linear. There is some amount of noise, but we can clearly see that there is a straight line like this which fits through the data. For such data sets, traditional regression methods are very good and you can proceed with those. But what about non-linear data? What if the data set is like this, where there is a cluster of points here, then there is a cluster of points here, then here, and then here? Try fitting a straight line here. No matter which straight line you use, it will not fit this non-linear data very well. It is in this type of data where regression trees are actually extremely beneficial and extremely useful. In today's lecture, let us understand what regression trees are and what type of problems can they solve. And from the next lecture, we will start building out regression trees. So again, as a reference, I am following the lecture material on the Stats Quest channel. I have distilled this material down into building blocks, but I'm a big fan of this channel. So just giving credits here. So the problem which we are going to solve is this. We have a training data set which consists of drug effectiveness on the y-axis and the dosage of the drug on the x-axis. So imagine a data set where you have the drug dosage such as in terms of percentage. Uh, so 10, 20, 30, 40, etc. And on the y-axis, you have drug effectiveness percentage. So the goal is to kind of quantify the relationship between the dosage level and the drug effectiveness, right? So that whenever you meet a new person, let's say, or whenever a new person is administered a drug, uh, can you predict based on the drug dosage which they have taken, what would be the drug effectiveness? That's the main problem which we are trying to solve. And let's say the data set looks something like this. If you concentrate on the yellow points right now, don't focus on the orange line or the orange text. Just look at the yellow points right now. This is our data set right now. Here you can see on the x-axis we have the drug dose, and on the y-axis we have drug effectiveness percentage. And if you focus on the yellow data points, the first thing which you can see is that it's kind of in clusters, right? It does not look like a linear data set at all. In fact, if you try to fit a straight line through this data set, it's a very bad idea. So you cannot use traditional regression methods also. So let me erase this straight line here so that I can also tell a bit more features about this data set. So I've erased this right now so that uh, we can clearly visualize the data set. So traditional standard linear regression is going to be a bad idea, right? And one more way to think about this is that wherever there are points of high magnitude, such as these points, it's always surrounded with points of low magnitude, such as on the left and on the right. This is a perfect indication or a perfect representation of a data set which is not ideal for linear regression. Such kind of clusters, which you can see in a non-linear manner. And to solve this problem, we are going to use a regression tree. It turns out regression trees are much better than traditional least squares to solve problems like these. The other advantage of regression trees is that regression trees are also very easy to interpret and use. So the first advantage which I told you about regression trees is that they can handle non-linear data in a much better manner, right? Compared to other regression methods. But there is another advantage, and that is that like with all decision trees, they are very much interpretable in nature. One thing which I really respect and I really like about decision trees is that unlike other neural network methods, regression trees are highly interpretable. You can look at a regression tree and can ask questions that why is the answer like this or why is the solution behaving like this. It's like shining a torch on the black box, which is usually machine learning. Great. So let's use regression tree. And our aim is that given a new dose, can we actually find the effectiveness of the dose? So we have this training data, right? If we are given a new data which is not in the training, which is a new dose, Can we find the effectiveness of that particular dose? That's the problem which we are trying to solve. Before building out a regression tree, I first want to show you what a regression tree can look like, and then you will get an understanding of, or you will get a roadmap of what we have to build in this lecture series. So, this is how a typical regression tree actually looks like. If you look at it in detail, you will see that it's kind of similar to a classification tree, but now there is like a numerical data over here. So you must be thinking, right, how are we going to represent numerical data like this? Because it's also continuous data, it takes value between 0 and 100, the drug effectiveness level, right? How are we going to represent this in the format of a regression tree? So very similar to classification tree, the first thing you notice is that we have a root node over here. We have a root node over here. Then we have, these are also called as intermediate nodes or branches. So we have branches over here. This is also very similar to classification tree. And then finally we have this, and this, which are the four leaves. These are the four leaves which are there. Now, as we looked at a decision tree, it has two main things, right? It has a statement and then it splits into decision. So that statement in the case of regression tree is to do with numbers. So dose is my x-axis, right? So at every statement which you see, dose less than 14.5, dose greater than or equal to 29, dose greater than or equal to 23.5, all these statements are comparing the dose with a particular amount. So right now, don't worry about how I constructed this regression tree. Our whole purpose of the next lectures is to build out such a regression tree from scratch. Right now, I just want to show you how it works. So this regression tree says that, let's say you are given a new patient and that patient has certain amount of dosage. What you do is that you first check whether the dose is less than 14.5. If yes, we are going to conclude that it's 4.2% effective. If no, then you check whether the dose is greater than or equal to 29. If it is indeed greater than or equal to 29, then we will conclude that it is 2.5% effective. If the dose is actually less than or equal to 29 but greater than 14.5, we check whether it is greater than 23.5. So this yes branch here is actually the dose lying between 23.5 and 29. So if it's yes, so if the dose lies between 23.5 and 29, we will say that it's 52.8% effective. Whereas if that is also no, which means that the dose actually lies between 14.5 and 23.5, then we are going to say that it is 100% effective. This is how the regression tree looks like. And let's actually test whether it makes sense for our training data over here. So why does this tree make good predictions? The reason is because each leaf in the tree corresponds to a different cluster in the graph. When I say leaf, it means these questions, right? Dose less than 4.5, this leaf. So this leaf belongs to one cluster, this leaf belongs to one cluster, this leaf belongs to one cluster, and this leaf belongs to one cluster. Let me show you what I mean. Okay, so let's look at the graph again. Um, okay, so this is the training data graph which we have, and now let's look at the root node. What the root node is saying is that dose less than 14.5. If it's yes, it's 4.2% effective. So let's see where dose is less than 14.5. It's in this first cluster over here, right? In this first bounding box which I've showed here, the dose is less than 14.5. Look at the x-axis. For all of these points, the dose is less than 14.5, and for all of them, the value is close to 4.2%. That's why we are very confidently saying that if dose is less than 4.14.5, the value of the drug effectiveness is 4.2%. Great. Now let's look at another cluster. So now let's look at if the dose less than 14.5 is no, which means we go over here. Now let's look at dose greater than or equal to 29, which is this second leaf. Let me mark it with a different color so that it's visible. So we covered this first leaf over here. Now let's look at the second leaf, which is dose greater than or equal to 29. And we are saying that for all dose greater than or equal to 29, the dose is 2.5% effective. So let's see where greater than or equal to 29 is. It's this box over here. So this is where dose greater than or equal to 29, it's this cluster, and we are saying that the effectiveness is 2.5%, and that indeed makes sense for this entire cluster over here. Now let's look at the further branch. Let's look at, so now this leaf is done. Now let's go to this branch, which means dose is greater than 4.5, but dose is less than 29. And then we further classify and go to this branch. So this branch means that dose is actually between 23.5 and 29, this branch. So let's see which cluster that belongs to. So dose is between 23.5 and 29. So it actually belongs to this cluster, these 4 points over here. And look at their y-axis, it kind of between 50 and 60, right? So we are very confidently saying that the drug effectiveness level is 52.8%. Note that it's not like standard regression where every point will have a different value, but we have windows. So, for example, 23.5 to 29 is one window, and we are saying that for all the points belonging to this window in the x axis, that is the dose, the value of the y axis, which is the drug effectiveness, is going to be 52.8. And finally, let's look at the last. So, now this leaf is also done. I'm going to put a tick mark over here. Now, let's look at this last leaf, which means that the dosage is also less than 23.5, but the dose has to be greater than 14.5. So this last branch is actually the dose lying between 14.5 and or rather 14.5 and 23.5, and here we are saying it's 100% effective. So let's check whether this is actually true. So dose lying between 14.5 to 23.5, it's actually this cluster over here. And we do see that indeed for all the points in this cluster, the drug effectiveness is close to 100%. So this is the fourth cluster and the fourth leaf. So you can already start seeing the intuition which we are building here, right? Every leaf in the decision tree, or rather every leaf in a regression tree, actually corresponds to one cluster. So the data set itself can be broken down into four clusters. This is cluster number one, this is cluster number two, this is cluster number 3, and this is cluster number 4. The reason the final regression tree has 4 leaves is because there are 4 clusters in the dataset. So decision trees are equipped to deal with clusters of non-linear data, which regression or ordinary least squares methods are actually not equipped to do. And that's one of the fundamental reasons why regression trees are used for problems like these. Of course, there are some drawbacks here, like as you can see, we are not predicting continuous value, right? We are looking at windows like 14.5 to 23.5, and we are saying that for all x within this window, the y is a specific value. That is the only drawback. uh, Apart from that, decision regression trees are actually very powerful for solving regression problems, especially with non-linear data. So the COVID-19 data set, right, which we earlier looked at, this also contains non-linear data, and that's why there were so many submissions of this COVID-19 forecasting with regression trees. So it's very important to know the concept. So I hope that until now you have understood how an optimized regression tree looks like. What we'll be doing from subsequent lectures is to build out this regression tree. There are so many questions, right? So if you look at this regression tree, how do we build this out? So first, how did we come up with 14.5 here? How did we come up with 29 here? All of these are open questions which we'll start to address. When we were building classification trees, we also spent a lot of time discussing how to fix the root node, right? Similarly, we'll be doing for regression trees. How to decide the root node, how to decide the branches, how to finalize the leaves. And similar to classification trees, we need a metric to quantify the purity or impurity of the leaves. In classification trees, that metric was Gini impurity or entropy, but in the case of regression trees, that metric is going to be different. It's going to be the squared sum of the errors, and we'll also look at that. So, all of this we'll be covering in the next lecture. In today's lecture, I wanted to give you this intuition of how the optimized tree looks like and how the leaves of the tree correspond to each of these four clusters. So this brings us to the end of this lecture. I hope you are ready to build out an entire decision tree from scratch from the next lecture onwards. And then we'll also look at the Python coding like we did for classification trees. So as always, the goal of these lectures is to build everything from scratch, not assume anything, show you the fundamentals on the whiteboard, plus at the same time take you to the code later. This is exactly what we will be doing with this regression trees set of videos. So thank you so much everyone, and I look forward to seeing you in the next lecture.